Welcome. In today's lecture, we want to understand the phase field modeling, the first equation that we write for doing phase field modeling, which is known as the Cahn-Hilliard equation. For doing that, we are going to go back to the thermodynamics, we are going to write the free energy functional, and from there we will try to derive the Cahn-Hilliard equation. For doing that, I would like to remind of some of the things that we have discussed in the past. Let us consider the two phase equilibria, for example. We have seen that using a simple regular solution kind of model, one can see that when there is two phase coexistence, the free energy versus composition curve looks like this in a binary alloy, right. So, you have something like this and you have something like this. So, we have a common tangent construction and the points. So, this is free energy, this is composition, and this is for example x b alpha, this is for example x b beta. So, if you have some alpha and beta phase, the equilibrium compositions of the alpha and beta phase are given by this, if this is the free energy versus composition diagram. Now, if you for example go across this line and plot the composition. So, in alpha phase it is going to be the x b alpha, and wherever is the interface, and beyond that it is going to be x b beta. Now, what happens at the interface is the question. So, many of the classical models take this composition in alpha phase to be x b alpha up to the interface and x b beta to be x b beta up to the interface, and the interface is a plane of discontinuity. Now, in this picture, if you look at the free energy, so free energy is a minimum because this is the mechanical mixture free energy. So, if you have these two end compositions, the free energy will lie somewhere here. However, there is a problem with this kind of assumption, because we see that there is a discontinuity in composition. That means there is a sudden change in composition, and that can actually contribute some energy. To understand this better, for example, if suppose I said that up to this plane it is x b beta, and there is an intermediate plane which has composition which is an average of these two compositions beta plus x b alpha by 2, and from here it is x b beta composition. So, the interface is something like this. Then there is this x b beta plus x b alpha by 2 region. So, that composition is going to lie somewhere here. So, there is a cost associated with making the interface more diffuse instead of keeping it as very sharp, that comes from the free energy itself. So, this is the classical free energy. But what the classical free energy misses is that if you assume that the beta and alpha compositions are uniform throughout the phase, then at the interface there is a discontinuity. That discontinuity will contribute to the free energy. Even if you have a continuous composition curve, the gradient then will start contributing to the free energy. This gradient contribution has to be accounted for. The way we are accounting for is that, for example, this free energy is a regular solution free energy, right. So, you can get it by having the regular solution free energy as x into 1 minus x plus R t x log x plus 1 minus x log 1 minus x, okay. Something like this, plus G A plus G B x G A 1 minus x G A plus x G B will actually give something like this. So, in this we are only considering the composition, and only composition is contributing to the free energy. So, this is a free energy function, and you can take the derivative of the free energy function with respect to composition, you get what is known as the chemical potential. But a problem with this kind of model, especially when you have two phases, is that we are assuming a constant alpha composition, constant beta composition in the alpha and beta phases, and interfaces have discontinuity in composition. and this is also not acceptable from a purely thermodynamic point of view, because once you have set down the thermodynamic parameters like temperature, pressure, number of atoms, composition, etc., then there are no other information that one needs to specify. The system will choose, for example, whatever interface width it wants to choose. It is wrong to arbitrarily assign it to be a plane of 0 width or one atomic plane or several atomic planes and so on and so forth. So, to avoid this is why we are looking at the modification to the free energy, and the modification to the free energy comes from Taylor expanding the free energy by assuming that the free energy is function of x, y, z positions, because we are assuming that the free energy is going to be not homogeneous and constant everywhere. So, its composition, and we are going to assume that it is also and the second derivative is del squared c by del x squared, del squared c by del x del y, del squared c by del x del z, and so on. That is a free energy functional, because now the free energy is not just a function of composition, but also its gradients and curvature and so on, and that is written as an integration over volume. And so we have this free energy F, and this F dV that we have. So, this F I am going to write as a Taylor series expansion by expanding. So, I am going to consider a composition, some nominal composition of C, about which there are some changes. So, I am going to write the free energy for such a system. So, F for this such a system is F of C, where C is the nominal composition. So, if there were no composition variations positionally, if you have uniform C composition, what is the free energy? That is the first term, and then I have the Taylor expansion terms. So, the first term is dou F by dou del C dotted with the del C, and this is a first rank tensor. So, let me call it as alpha I. So, to indicate that, so because this is now vectorial notation, I will also call this as del C I, meaning that this is dou C by dou x I. In a similar fashion, I have the second term, which is del F by dou del squared C, and again I j, then it is two inner products with del squared C I j. The notation again meaning del squared C I j means dou squared C by dou x I dou x j, that is what this means, plus 1 by 2 factorial del squared F by dou del C I dou del C j, again two products with del C I del C j and so on. Okay. So, this is the free energy functional that we are going to put. So, this is the first rank tensor I am going to call alpha, this is a second rank tensor that I am going to call beta I j, this is another second rank tensor, I am going to call this as gamma I j. So, in this fashion we can now write the free energy functional as follows. This is f of c plus alpha I del C I plus beta I j del squared C I j, where we are assuming the Einstein summation convention, plus gamma I j by 2 del C I del C j plus so on. So, the total free energy is nothing but F dV. So, this is the free energy functional. Now, we are going to use some of the properties that we have learnt about tensors properties and their representation in crystals. First thing to assume is that we are in systems in which there is a center of symmetry or inversion symmetry. So, all odd rank tensors in such systems is going to be 0. So, alpha I is going to be 0 because I am assuming inversion symmetry. The other way to also say that this term is 0 is to say that we are going to look at free energies which are going to have a minima at some C value, and about the minima then the condition would be that you can't have any such first rank terms, because they will change sign if you go either way. But suppose if you take very small changes in composition, these terms are not important, then this term will be positive in one case, negative in one case. So, you will not get minima if you add this term. So, you want to make that 0. So, that is another way of arguing about the odd rank tensor going to 0, the vector term going to 0. Now, if you look at these two terms, then it is possible to make them both in the same form as this. So, how do we do that? To do that, let us consider this beta I j del squared C I j, that is nothing but beta I j del squared C by del x I del x j, that is dV. So, this is the integral, and so I am going to make this as beta I j dou by dou x I of dou C by dou x j, right. So, we know that this term is nothing but del C of j. So, I am going to write this. So, this is the term we are looking at, beta I j dou by dou x I of del C j dV. So, that is nothing but so you can write this as beta I j del C j, which is evaluated at the surface, minus integral dou beta I j by dou x j del C dou x I del C j dV. And suppose if you are interested in an infinite system, or you are not interested in what is happening at the surface, or you will choose the surface for your volume in such a way that the opposite surfaces will give equal contribution. So, there are several different ways in which you can make this term go to 0, and we are going to assume that this is identically equal to 0. So, we consider this, and this can further be written as minus dou by dou C of beta I j and dou C by dou x I and del C of j dV integral. So, if we substitute this back into the free energy, so we see that my f is equal to integral f of C, the first alpha term is 0, that we already argued. So, then I have this gamma term plus gamma I j by 2 minus this term dou beta I j by dou C multiplying delta C I delta C j total dV. This is the free energy functional we have, and I am going to replace this quantity by some kappa I j. Okay. And this other higher order terms also I have neglected. So, my free energy functional happens to be this f of C plus kappa I j del C I del C j. So, this is the free energy functional I have, and I am going to now assume cubic systems in which this is a symmetric second rank tensor, because kappa I j is equal to kappa j I, that is because it does not matter whether you take del c I del c j or del c j del c I. So, it has this intrinsic symmetry. So, such symmetric tensors in cubic systems, second rank tensors, they will also be isotropic. So, that we have already seen. So, I can further reduce this to f of c plus some kappa, which is a constant, delta I j, del c I and del c j. So, dV. So, that is delta I j acting on this is going to make it delta c I delta c I, and if you use Einstein summation convention, again that is nothing but f of c plus kappa del c squared dV. This is the free energy function. So, what we now have is the free energy functional, and it is a free energy functional. So, the independent variables x, y, z are not explicitly appearing here. C is a function of x, y, z and also time t, and del c is the gradient on c. So, we have a functional which depends on a variable c and its gradients. So, we can write the Euler Lagrange equation. So, the minimization of free energy means that you can take the variational derivative of f with respect to c. This quantity is nothing but the chemical potential, because remember in the case if g is a function, then dou g by dou c is nothing but mu 1 by n, right. 1 by n, because dou g by dou n b is mu, and so the by n, if you put and multiply by n, so that becomes c. So, that is the reason. So, we are going to use the same thing. So, 1 by n del f by del c is the chemical potential. So, what is del f by del c? That is obtained by the Euler Lagrange equation. What does it say? So, if you have a functional which is like, because f is equal to f of c plus kappa del c squared dV, when we take del f by del c, that is going to be dou f by dou c minus del acting on this quantity. So, differentiated with respect to del c. So, when you differentiate, this is the only term that has del c. So, 2 kappa del c, this is what you get. And if you assume that kappa is a constant, you can pull it out. So, you get dou f by dou c minus 2 kappa del squared c. This is del f by del c. So, if you the mu n mu is nothing but this quantity del f by del c. So, that is dou f by dou c minus 2 kappa del squared c. So, this is the first term. So, we have obtained the chemical potential in the case of a functional. So, we went from a function for free energy to a functional for free energy. That is because free energy was initially only a function of composition. Now, it is also a function of the concentration gradients, composition gradients. That is because we want to incorporate the contribution from the interfaces. Interfaces are regions where composition changes from one value to other value. Bulk system, bulk phases are phases where the composition is uniform. So, interface contribution is then incorporated by incorporating the gradients and any higher derivatives. So, to get the free energy for such a system which has compositional heterogeneities, we Taylor expanded and produced a free energy functional, and by taking the variational derivative of that free energy functional with respect to composition, we get the chemical potential. Once we have the chemical potential, of course, we know how to get the diffusion equation. So, we will go back and do it. So, initially we said that the flux is minus m del mu, where mu is the chemical potential, and now and dou c by dou t is equal to minus del dot j and so putting together dou c by dou t is nothing but del dot m del mu. Let me further assume that m is a constant. So, m del squared mu, and we know the mu value. Okay. So, n mu value. So, I am going to have this n pulled out. So, we will have 1 by n dou c by dou t is equal to m del squared acting on dou f by dou c minus 2 kappa del squared c, and so that you can write it as m del squared dou f by dou c minus 2 kappa m del power 4 c, assuming that kappa again is a constant. So, we get an equation which is the modified diffusion equation. Okay. Suppose if we incorporate this the free energy that we wrote in terms of per atom, then one can get rid of this n term. So, we will get something that looks like that. Okay. So, assuming that the free energy that I wrote is for the entire volume, I divide by the number of atoms. So, I get per atom free energy, then my diffusion equation, the modified diffusion equation that I derived becomes m del squared dou f by dou c minus 2 kappa m del power 4 c. So, this equation is known as the Cahn-Hilliard equation. This is a modified diffusion equation, that is not very difficult to see. To see that it is a modified diffusion equation, let us consider this del squared dou f by dou c term, where it comes from. The first one is in del mu. Okay. So, mu had this dou f by dou c term, and when we acted del on this, so there is a way to write this. So, you can write, so del is nothing but, for example, if it is 1 d dou by dou x, suppose if you had dou f by dou c, then that is the same as the del squared f by del c squared dou c by dou x. So, how do we do that? So, when I take dou by dou x, I can write it as dou by dou c acting on this times dou c by dou x. Okay. So, that is what this term. So, f dou f by dou c, which is the curvature of the free energy versus composition curve. So, that I can call this as f double prime. Remember, when we defined spinodal, where this quantity became negative is where the spinodal regime was. So, this is the curvature of the free energy curve. So, I am going to assume that this is a constant. If you do that, then when you put it back here, so you have f double prime dou c by dou x and another del acting on it. So, you will get dou c by dou t as m f double prime del squared c minus 2 kappa m del power 4 c. Now, m f double prime is the diffusivity. That is why when f double prime became negative, diffusivity became negative. When it was positive, m f double prime was positive. So, you can explain both the cases, namely downhill diffusion and uphill diffusion. So, if you look at this part, dou c by dou t is d del squared c is nothing but the classical diffusion equation, and what we have here is a modification to the classical diffusion equation. In fact, it is a modification which incorporates higher order derivatives in composition. So, you can think of Cahn-Hilliard equation as a modified diffusion equation, the modification being in addition to del squared c, you have a del power 4 c term. Now, what is the effect of this and what happens is something that we will discuss, but at least from here it is very clear that this term has with this negative sign is the term, and the kappa came from concentration gradients, and concentration gradients represent interfaces. So, this is a term that is related to the interface, and so the interfacial energy related effects will be incorporated through this term. That means the contradiction that we saw when you were solving the classical diffusion equation, that you start with a spinodal system, phase separating system, but if you solve the classical diffusion equation you get the solution that it orders. That will be taken care of by this higher order term, because this now sets a limit to the lower wavelengths. So, beyond some system size, if you try to increase these composition fluctuations, that is, if you make A rich regions A rich and B rich regions B rich, and if the regions that you are trying to enrich are smaller than some length scale, then the interfacial contribution, namely that AB bonds are not preferred and their energy is going to come into play. So, they are going to the regions of A rich and B rich regions that would grow, or the wavelength of any such disturbance that you have that will grow, there is a lower wavelength limit. So, that is basically set up by the interfacial energy. In this system, now we can also understand the interfacial energy as follows, or the interfacial width as follows. So, we have this. So, the f of c could be a curve which is of this type. Okay. So, it has these common tangent points. So, if you have a system which has alpha and beta, so there is a region over which the composition changes over, and so if you go across a line like this and if you look at the composition, the solution to the diffusion equation that we have written is going to be like this. Okay. So, this is x b beta, this is x b alpha, where this is x b alpha and this is x b beta, and this region where you have this composition, this thing is the diffuse interface. Okay. This is where the name diffuse interface approach or diffuse interface models comes from. And what determines the thickness of this region? It is determined by this barrier height and the kappa. Why? Because suppose if this barrier height is very high, then if you try to set up a concentration gradient which is very shallow, then the energy cost associated with having compositions in between these two endpoints is going to rise very high. So, this is not preferred. On the other hand, if you make the concentration take a discontinuity here, the del C term which goes to infinity, because there is a discontinuity, that contribution to free energy is going to become very high. So, the system is actually going to choose an interface width in such a way that whatever is the kappa, the gradient energy coefficient, whatever cost it has to pay for this, and that, so that means there are going to be compositions which are all over these points, and they are going to increase the energy a little bit, and it is going to gain some energy from this interface part. So, the competition between the two, the balance between the two is going to determine what the interfacial energy is going to be automatically from the system. So, once you have written the free energy functional, once you know what this kappa is, and in the f of c, which is where this term comes, the barrier is determined by f of c. So, once this is fixed and once kappa is fixed, the system will take an interfacial width that is going to minimize the given free energy. So, we have now derived the first phase field equation or diffuse interface equation. This is known as Cahn-Hilliard equation. Just to remind ourselves, in terms of the derivation, it is the same as we derived the diffusion equation. So, you first assume that the flux is proportional to chemical potential gradient instead of concentration gradient. So, that is the first difference, and then you use continuity equation, you get a diffusion equation. So, Cahn-Hilliard equation or phase field equation is just a modified diffusion equation, which is obvious because we are looking at concentration evolution. So, it will be a diffusion equation of some sort. And the second difference is that the chemical potential is not derivative of the free energy with respect to composition. That is classical thermodynamics. In this case, we want to incorporate the interfacial effects. So, we have some non-classical thermodynamics, in which the free energy is not just a function of composition, but it is a functional. So, it has composition and its gradients, and sometimes even the curvature terms and aberration terms or any other higher order derivatives of composition with respect to position as independent variables. So, you write a functional instead of a function. So, to get the chemical potential, you have to take a variational derivative instead of just taking a classical derivative, a partial derivative. So, this variational derivative gives the chemical potential, and that chemical potential is now put back into the constitutive law, namely that flux is proportional to chemical potential gradient and the constant being the mobility, and you put them back, you get the equation. Of course, we have made certain assumptions. We have assumed that the material we are considering is having a center of inversion. So, that is the and that can also be motivated through other means. You can also say that because I am looking for some minima to be there in my system, the first derivative terms will not be there. So, there are several ways of motivating that. The second most important assumption that we have made is that I am considering a cubic system. So, the second rank tensor became isotropic. So, isotropic system also it will hold. But if suppose this was not a cubic system, then there is no necessity that the coefficient, the kappa ij, has to be isotropic. It can be isotropic. Neumann principle does not rule out. Suppose it is tetragonal, for example, isotropy is much better symmetry, or it is a larger symmetry. So, the minimum it should have is tetragonal. It can be better than that. So, it can be cubic or isotropic. It cannot be worse than that. So, that is what it means. So, you can have a tetragonal system, and in which case it need not be isotropic, which means the c axis will have different values from A and B. The property along c direction will be different from the A and B, in which case you will see that the kappa ij in such a system is that kappa 1 and kappa 2 might be equal, but kappa 3 is not equal. So, you will get a difference in terms of the constant that goes into the free energy functional. Otherwise, the formulation is the same. All that the cubic assumption got us was that it made the term that is multiplying the delta C as a isotropic term. It is not necessary, and when you have this general free energy expression where delta Ci or the independent components, how to write the variational derivative is described in the book that I referred to earlier in Shames and Dim, energy and finite element methods in structural mechanics. So, one can write the most general expression and write the chemical potential by taking the variational derivative, use it to get the modified diffusion equation. So, that part is common. The assumption or approximation we made that we will consider cubic system is only to make the algebra a little bit simpler, but so without loss of generality. The same procedure can be used for systems which are not cubic also. So, we will stop it at this point, and now that we have derived the equation, the next step is to go ahead and solve it. So, we have solved the diffusion equation using spectral techniques. So, we will use similar spectral techniques to solve this equation also, and see how the solution looks and how the solutions are different from that of the classical diffusion equation. So, that is what we will do in the next lecture. Thank you.